everyone. I am Luca Tedesco, aka QWERTY or UIOP. And I've actually given this talk already, sort of. I've changed some stuff here, but there was some technical issue the first time I gave this talk, and so when the video was recorded, my voice was dubbed in Chinese, and it was kind of a issue because I believe the talk is very interesting, and many people were not able to understand it due to that. So, life as an iOS attacker. As I mentioned, I am Luca Tedesco, aka QWERTY or UIOPZ. It's a tricky nickname. I do lose my passports fairly often. I am actually employed, self-employed if that counts, as an iOS security researcher at KJC International Research SRL. I've owned an iPhone since iOS 2. I was a very young kid, and I was really into this thing called jailbreaking back then. And come around iOS 10.2, I actually released my first public jailbreak that was widely used. I have released previously some minor public jailbreaks and contributed to other jailbreaks. But the 10.2 one was my first big one, and probably last one for a while. And as I mentioned, I already gave this talk in Shenzhen at Tencent, and I added a bunch of things. And if you want to get in touch with me, you can get on irc.cracksby.kim when the server is not down. So today I'm going to discuss about the iOS security design and the historical things that made the iOS security design what it is today. And I'm also going to discuss about how an iOS attacker will think. And I'm going to discuss about one-click exploits, which I believe to be the best long-term scenario for iOS attackers. And I will also discuss about the new iPhone XS and XR, XS Max, which bring a new architecture with a different ABI than before, which has pointer authentication, which is a fairly new feature to enforce CFI in a different way than, say, Microsoft does it. As well as some extra hardening for PMAP, which I'll tell you what it is later. And I will give my personal opinion on what the future of iOS attackers is. So back then, on the very first version of iOS, there was absolutely no security, no ASLR, no DEP, everything ran as root, no sandboxing, no code signing, no secure boot. Well, there was some secure boot, but it was fundamentally broken, and no third-party apps. This was a big deal because people realized that native third-party apps were a big deal, yeah. And so people try to modify their phones, and these spawned a community called jailbreaking. And back then, things were really simple. However, very, very, very early on, somebody actually came up with something called Jailbreak Me, which allowed people to jailbreak their phone by just visiting website. And this is sort of the model that now is called one-click. And even a few Apple employees apparently were involved with the jailbreaking community at first. But things change really quickly as soon as the threat model for Apple becomes DRM. So the big issue is that they actually released their own app store, and they were selling apps. And by being able to modify your phone, you would very easily decrypt those apps and redistribute them. App piracy was very, very, very rampant on desktop operating systems. So in my personal belief, I'm not entirely sure if that's the case, but code signing was introduced to try to prevent the piracy scene from taking over the iPhone platform. And I believe that it was the only real threat that Apple considered back then. And from there, a cat and mouse game started, where Apple kept learning what attackers would do and push new updates that would harden the iOS security model. And over time, these pretty much ended up with three big things. So first of all, the bootloader used to have a lot of debug features. Now on a release device, the bootloader is fundamentally very small and doesn't have many degrees of freedom, which are useful in case you're an attacker. Additionally, ASLR and DEP were introduced very early on. I think it was around iOS 4. And additionally, on the very first models of iPhones, you would be able to downgrade the firmware to a vulnerable version if you so wanted to. These allowed you to reuse bugs across one specific generation device over and over without having to find new ODE. However, initially they used to rely very heavily on security by obscurity, and they still do in some case. For instance, the secure enclave processor is still running on an encrypted image, and people have posted decryption keys online. So if you actually wanted to look into the SCP, you can, but Apple still refuses to give you visibility on the later versions that have not been publicly decrypted. However, things are changing with the kernel and a bunch of other things in the firmware that are now decrypted since iOS 10. And the kernel sources were also published recently, and there was a pretty bad leak of bootloader sources back then. So there's a lot of knowledge out there by now. And downgrade protection really doesn't actually provide any security to people that don't want to get their phone hacked, because you can just run the latest firmware. And I believe it's still an artifact of the historical DRM threat model that is probably not so historical and still matters to Apple's business. And also, they try to make it very hard to debug your kernel or anything except your own app, which obviously makes the work of security researchers harder. And so the solution for that is to develop iOS attacks to bypass those restrictions and to carry out more security. And this starts the iOS attacker model. So initially, I believe most of the research was actually done due to the need of jailbreakers. So these are actually attackers that Apple might really dislike, but I believe are fundamentally positive for end users as they add more choice. However, as the game gets tougher and more people start looking into these new mobile platforms, attacking iOS for intelligence gathering and law enforcement became more and more popular. And I believe these attackers do not actually affect Apple's bottom line that much, but could be negative to end users in some ways. And these attackers actually want multiple things. There's remote and physical capabilities. Remote capabilities, you have one click, which I believe to be the best long-term solution for iOS attackers. And then you have zero click, which will rely instead of system services, messaging apps, Bluetooth. And you can even rely on something like XSS in order to then chain load a one click and turn it into a zero click. Additionally, people are also interested in physical attacks. So you're going to have evil maid attacks and in-transit device tampering, where somebody will swap your device out as it's coming to your mailbox. And data protection attacks for forensic analysis, which every single one of these will require a different kind of research on iOS. So usually, if you specialize on one of these, like one company will only specialize on one of these. Very few companies will do multiple at the same time. Individual researchers will actually specialize on only one aspect. And by one aspect, I mean even less than that. So, just one vulnerability or kernel privilege escalation. And they will then figure out a framework to find multiple of these vulnerabilities, which will likely end up in an offensive company, which will chain those vulnerabilities together into an exploit chain, which will be able to load code at the wished privilege level. The most common privilege level which is sought after is obviously kernel mode, but it's not at all necessary in order to accomplish those tasks. And people will develop post-exploitation toolkits that will allow for, yes, data exfiltration, those sort of things. But this is kind of far, I believe, from the work of researchers themselves, and it's a few steps down the chain. And eventually Apple will kill some of the bugs, and so you have to go back to the very top and find new vulnerabilities and integrate them with your current toolkit, or make a new toolkit in case the one you currently have is not capable of using your new vulnerabilities. And yeah, repeat. As the level of difficulty in compromising iOS goes up, persistent attackers that already have capabilities right now can easily play catch up, because you will have incremental security upgrades. And new players might feel all the pain because they have to start from zero and get acquainted with every single mitigation that Apple added so far. And I think Halvar discussed this in a more general context. It's a nice talk. You should check his talk out. And the typical one-click exploit chain, again, I'm pretty sure I said it 3 times already, but I think it's the most likely to be long-term viable capability. Web browsers will always have vulnerabilities. And again, you can use XSS in order to turn it into a zero-click if you so wish. And it usually will involve the combination of a WebKit vulnerability and at least one privilege escalation vulnerability, even if 2 or more are common as far as privilege escalation goes. And the WebKit vulnerability must be powerful enough in order to derive an info leak, and on recent devices you will also need the arbitrary read primitive if you want to go anywhere. Heap spraying is viable. The randomization on iOS is actually pretty bad. I do not believe any serious attacker is going to rely on heap spraying. I hope not, but it's one possibility. And DEP can bypass the ROP, or data-only exploitation. Data-only is the best alternative because it's actually a lot easier to maintain over time compared to ROP, and it can actually be more powerful if done correctly. ROP can be exploited in a simpler way actually at times, but will require constant iterations on top of your exploit on every single binary layout that you want to target. And it will be necessary to use ROP on some vulnerabilities, but I actually recommend to use those for pwn-to-own, and if you're actually trying to be an advanced iOS attacker, look for better bugs. Once you have the ability to read, write, and execute, the next stage is obviously to load shellcode. iOS has mandatory code sign checks, so you can't actually just load a library or something along the lines which might be done in other contexts. However, you do have an area of memory which is used by the JIT engine, and you can just write your payload in there, invoke it, and back in iOS 9, that was all you needed to do. Until Apple introduced this one feature called bulletproof JIT, where in order to write your payload in JIT memory, you are actually forced to do a function invocation. And they do this by having 2 different maps, where one is writable and one is executable, and the backing physical memory is actually the same. However, the writable map does not have any pointer to it stored anywhere in the address space, except in a very small stub, which is execute only. So you cannot actually leak that pointer. You can guess it. You can invoke the small stub in order to write to the executable side. But with the A11 CPU, Apple actually introduced silicon changes that will turn your read-write-execute memory into either read-write or read-execute based on a system register which is set only by the JIT engine in specific points in time. And so if you actually want to touch JIT memory, you are forced to invoke a function, which is not really an issue, or wasn't, at least until the last generation of iPhones. And this actually pointed me towards the fact that Apple might be introducing control flow integrity. And I actually discussed about possible ways to attack control flow integrity in 2017, only because I could infer that it was about to come, thanks to this feature. And anyway, let's keep going on our iOS exploit chain. You'll have your shellcode, which some might write as raw shellcode, but that does not scale if you're actually writing an entire kernel exploit. It's not going to be easy to do it in simple shellcode. You're going to want to link to things. You're going to want to use a SDK, which is powerful enough to express what you want to do. And realistically, you can ask the dynamic library, the dynamic linker, to load it, your payload. But iOS does not actually have any feature to do that. macOS does, but it was stripped from iOS. However, when you run a binary in iOS, the kernel will actually map the binary in, and the dynamic linker will be invoked in user mode in order to load the main executable once it's already in memory. So what you can actually do is invoke the dynamic linker as if the kernel were invoking it. And this will actually load arbitrary libraries as if it were a normal Mako file. And it's pretty powerful in order to do iOS jailbreaks over WebKit. However, you will not be able to do easy process continuation. So this is not an effective strategy in case you're trying to do advanced attacks. So I ended up writing my own dynamic linker in JavaScript that will link in a payload which is compiled with the normal iOS SDK, map everything over, and yeah, with enough memory corruption, JavaScript can truly do everything these days. And user mode privilege escalation can be accomplished by reusing the ASLR leak from WebKit, as every single library in iOS is loaded at the same address and it's only randomized once per boot. And this is due to constraints on memory usage. So it's actually really easy once you have code execution in a non-privileged context to exploit even trivial bugs in other processes in order to gain more control over the system. Kernel mode privilege escalations will actually require kernel info leak, as any failure is fatal and your phone will reboot if you do not have the right slide. And the usual end goal of kernel code execution is to get read-write primitives from user mode, and you can use wrap-jump or data in order to derive those. However, most of this changed with the new iPhones. As I mentioned earlier, Apple added a new set of architecture features which can provide control flow integrity. And they call this internally ARM64E. They actually do both backwards edge and forwards edge CFI, building on top of ARM 8.3 authenticated pointers. And both kernel mode and user mode actually make use of CFI, which is surprising, as the ARM standard for authenticated pointers is not safe against a kernel mode attacker on devices without a hypervisor, such as iPhones. And it's not really fine-grained, it's not really coarse-grained either. It's somewhere in the middle, depending on what branch site you're jumping from. A brief description of pointer authentication is that ARM added new opcodes that will sign and authenticate pointers for you using secret keys that are stored out of address space. And you will check this authentication key every time you do an indirect branch, or every time you load some memory in a way that signals that you want to use pointer authentication. Additionally, you can specify a context on each pointer that you sign, which is a modifier of the key. And by specifying that context, you can make it so a specific pointer cannot be used in a different way than it's intended to be used. The algorithm that ARM suggests is QARMA, but I do not believe Apple is using QARMA. Maybe they are. I doubt that's the case. The backwards edge CFI will actually sign the pointer every time you enter a function, the return pointer, and then it will store it on the stack normally. And when you return from that function, it will validate the pointer before doing indirect branch in the ret. And you can see that the instruction is called retab, which means that they actually use the B key, which is a secondary key, and they will actually use the stack pointer as well as the context value. So if you have a stack frame and another stack frame, you're not actually able to swap return addresses between the two, but you need to have two stack frames of the same depth in order to be able to pull that off. So you might be able to carry out some pointer substitution attacks here, but I don't think it's a viable strategy. In C++ virtual call indirect branches, they will actually authenticate your vtable pointer first with the A key, and then they will use the pointer to the virtual function pointer as the context for the authentication on the indirect branch. And additionally, they will tag the context with a specific value, which I believe is per virtual call specific. And again, this all uses the A key. And I believe it's really difficult to pull off pointer replacement attacks here because, yes, every vcall will have a different context. But you might still have some leeway to do funny stuff with. Additionally, Objective-C is present in iOS. And when you invoke a method in Objective-C, you will go to this function called Objective-C message send. And it will get the class pointer from your object. And from the class pointer, there is a fast method cache. It will iterate the cache, and the only point at which the authentication happens is when you do the indirect branch, where the method pointer and the pointer to the entry are used in the branch, and the pointer to the entry is used as a context in this specific case. And you can note that they use the B key here. And I believe there might be tricks that can be pulled off here, as the only place where authentication happens is on the branch itself. And this is the simplest case. In a C indirect branch, they do not have any context and they cannot use any context. And they will use the A key for the branch. And you can see we just have a fetch for a function pointer and then a branch. And with this sort of scenario, you can actually replace your function pointer with any other valid function that might be invoked this way, and it will work. Additionally, there are some special cases and APIs in iOS which deal with pointers in ways that might not be normal ones. For instance, you have thread set context and pthread create, which will always use AZ keys, so no context and A key. So all these APIs might actually be used as invocation points for A key signed things. And kernel mode will actually have thread APIs that will also check against the A key, even if the A key in kernel mode and the A key in user mode are different. Additionally, there's some internal context saving stuff in the iOS kernel, which will store thread states when scheduling things out, and they use the G key in order to sign those. And pointer authentication actually has a few weak points. The number one strategy is pointer replacement attacks, where you will leak a signed pointer, and then you will reuse it in a different place as long as the key and the context is the same. Additionally, you will want to carry out a pointer forger attack at some point in order to be able to perform RUP and JUP. And to do that, you will have to find a signing gadget. Additional attacks might be brute force, which I do not consider viable in case you're an advanced attacker, because, I mean, it might be doable, but it could take several minutes to do it, and I do not believe that's a realistic time frame. Additionally, there might be key space attacks, but I doubt that Apple didn't consider those. Even if it does look like they only use 64-bit keys, I'm pretty sure they're doing some weird stuff in their silicon in order to add entropy. But I still do not believe that's realistic. I mean, 2 to 64 operations will cost you a lot, and it will take time. But maybe it's possible, I'm not sure. Control flow integrity will actually impact attackers in several different ways. The way C++ virtual calls are checked will actually, I believe, kill a lot of vulnerability classes. Webcore bugs, it's like dumb bugs, are very commonly used after free virtual call invocations. I believe those are very hard to exploit now, except for some special scenarios. And there's also IOKit, which is kernel mode C++ used in iOS that is also very prone to use after free. And again, I'm really doubtful that these vulnerabilities are now good enough to be exploited in most of the cases. But you can always find better bugs if you look hard enough. Additionally, we mentioned 2 different keys, key A and key B. The main difference between the 2 is that key A is actually shared across different processes. So once you have a key forgery, pointer forgery capability for key A, you will be able to reuse that for every single thing in the system. So this is actually really useful in case you want to perform a user mode sandbox bypass in order to elevate your privileges. Additionally, JavaScript core makes very heavy use of pointer authentication, and they will actually prevent a lot of trivial attacks. I believe in the latest few updates, they actually improved this quite a bit. Additionally, I believe some people might be thinking it's a good idea to replace stack cookies with pointer authentication, and I do not believe this is a good idea at all, as the return address is usually stored as the very last thing in a stack frame, while stack cookies can be placed surgically in order to protect known instruction pointer registers that might be spilled on the stack. And the biggest impact, I believe, that CFI will have in the world of iOS attackers is that it's going to make life a lot more difficult for the remote code execution step of it. And data-only attacks, I do not believe those are viable in order to be able to load your payload in JIT memory and do kernel exploits and your toolkit, however we want to call it. However, once you have a single valid way to jump into an unprotected pointer, you will actually be able to easily forge pointers from there. And additionally, you have a lot of entry points that are not recompiled against the new ABI, where pointer authentication is disabled, such as legacy apps. Handwritten assembly sometimes might use indirect branches without being protected. And you do have a JIT that you might be able to trick somehow into emitting an unauthenticated branch. If you actually wanted to go with a data-only way, the number one issue you'd have is the ability to issue syscalls from WebKit. However, iOS is actually designed around the concept of message passing, so syscalls are not the only thing you might want to do. And it's actually really common to be able to invoke the syscall MAC message once you have like any sort of app or daemon running on iOS. And once you have arbitrary read-write, you're actually able to rewrite the stack frame of a loop with MAC message in order to send multiple messages and possibly use this as a way to obtain pointer forgery. Additionally, a vast majority of the attack surface on kernel mode iOS, as well as user mode sandbox escape, is actually always reached through this syscall. So it's probably a good strategy, although I never try to do data only. I prefer forgery attacks. And for a real-life attack that was released very recently by Brandon Adzad at Project Zero, I will describe the way the attack will work, had worked. Yes, Brandon Adzad released his attack in January, and it's the very first pointer authentication attack known to the public. And it was released actually to get kernel mode code execution in a way that allows you to invoke arbitrary gadgets for his voucher swap exploit. And the trick he used is really cool. It's a really cool technique. And he started by looking for a signing gadget that you could invoke from a signed branch. Of course, there's no trivial ones that just lay around and allow you to sign whatever you want. However, there are some cases where the kernel will actually have to take a signed address and change the signature to a different context or key. And this is actually represented by a sequence of opcodes, the outi opcode and passy opcode, which will, the first one will actually authenticate your pointer and then strip the authentication code, and the second will overwrite the top bits of the pointer and put a new authentication code in them. And it looks straightforward. However, what if the first opcode fails the check? Well, it's not actually a branch or any indirect memory load, so it will actually do nothing. It will just set some extra bits in an invalid way, and it's going to hope that the next opcode, the passy, will take that into consideration and propagate the error further. However, it will do that by flipping a single bit after applying the valid signature on top of the pointer. So if you specify an invalid signature to begin with, you will get a signature which is also invalid, but just because one of the bits is. And so you can just flip that bit back, and now you have pointer forgery on ARM 8.3. His attack relied on a function in the kernel called sysctl unregistered OID, which will take a pointer and it will turn into a key signed zero context pointer. And you can actually invoke that as a legitimate part of the L2TP domain module stop, which happens to be a function for which there is a valid signed pointer present in the address space. So as long as you have a read primitive, you're able to link the pointer to that function and just invoke it with any indirect branch that has a key and zero context. And once you invoke this, it will actually store the result of the passy opcode somewhere in memory. You can just read it, flip the bit back, and yes, you can use this in order to sign a pointer to a branch which is not authenticated. And from there, you can just reuse that pointer over and over in order to branch anywhere you want into the kernel mode address space. Additionally, you can actually use normal job, and from there you can invoke another signing gadget, which might be more convenient to use. For instance, just invoking the passy opcode after the outi, and you will be able to sign pointers over and over with no effort. The attack was actually fixed by adding a failure case after the authentication instruction. However, the strategy can still be used today as a pointer validity oracle. The big issue is that the failure case is not fatal. While in a normal authentication use, such as memory access or branch, once the authentication fails, the pointer that is supplied to the branch or the load is invalid, and so the program will crash immediately. In this case, it won't. So even if the pointer is invalid, all it's going to happen is that it's going to not output a signed address. So if you just keep trying until you see a signed address as the output, you will, actually have pointer forgery all over again. And I think Brandon mentioned that these would take about 15 minutes, which, I mean, it's not realistic for iOS attacker, but it might be realistic for just personal use and research. But this is not the only thing that Apple changed in the new chips. There are some kernel mode changes to PMAP. And PMAP is the code that is in charge of keeping page tables in iOS. And page tables are actually involved in a bunch of code sign related tasks. And actually, the code sign kernel driver delegated a lot of trust related things to PMAP in iOS 12. And an arbitrary physical write would actually be able to just alter the page tables and skip all the code sign issues. However, Apple thought of that. And now, every single time that you want to touch the page tables, you actually have to invoke these functions, which are in their own code segment. Additionally, as I mentioned, adding trusted hashes to your kernel now requires calling into one of these functions in this pmap thing. And in order to enter any of those functions, you actually have to branch into a thing called PPL dispatch, which is a trampoline that will change a system register. And essentially, once you change the system register in a specific way, you're going to be able to alter page tables. Otherwise, every time you try to alter some of that data, the system will actually just crash. And yeah, you're not going to be able to inject code by just having a read-write anymore. Additionally, all the routines that are exposed will validate input to some extent. So you can't just create like a fake structure containing a fake set of page tables, but you must use real data that it actually keeps track of the structures that you're allowed to pass it. And once you enter PPL, you're going to run the first section of code, which sets a specific system register to a specific pattern, which is 4455, 4455, 6466. And you can see that when it exits, there is actually a small difference where the 4455 becomes a 4454. And that bit is in charge of telling the system whether you're in PPL mode, and PPL mode allows you to alter page tables. So I'm not sure why they chose that specific bit pattern, but additionally, once you encounter an exception, the kernel will actually check whether you're in such a special mode, and if you're in that mode, it will branch to an exception handler specific to that mode. So these would kill a bunch of tricks that you could use in order to bypass such a mitigation. But it is important to remind that everything is still in normal EL1, which is the equivalent of ring 0 as far as ARM64 goes. And it all relies on custom silicon logic implemented by Apple. It's pretty cool stuff, but the design does have weaknesses. However, it is a work in progress, and I do believe that the iOS game will get exponentially more difficult as time goes on to play. However, this specific mitigation is mostly significant for jailbreakers, because fundamentally, if you're trying to, say, gather data on somebody, once you get code execution as root out of the sandbox, that's actually all you need. You don't even need to go kernel mode. However, it does make rootkit attacks a bit trickier to pull off. And realistically, once you bypass CFI, you can still invoke the pmap functions in order to add trusted hashes to your kernel and load your own code without violating code sign. So what does the future have for iOS attackers? At the end of the day, I believe iOS attackers are fighting a losing battle. However, the rate at which the battle is being lost is very fast in some cases, very slow in others. And I always have a thought in the back of my head that tells me, hey, memory corruption is about to die in a couple of years. You're never going to be able to hack the new chip next year. But I've actually been thinking these for the past 3 years, and every single time, there was a way to carry on my research. And realistically, web browsers have so much complexity. Like, there is no way in hell web browsers are ever going to be secure. So I believe, life is going to be okay for people that do one-click, but zero-click scenarios will probably still survive for a while. But it's going to be more and more difficult as time goes on. And the rate at which zero-click is getting more difficult is a lot more difficult than one-click. Additionally, I do believe jailbreaks are likely to fade away at some point in the future, which makes me really sad, because I do appreciate jailbreaks a lot, and they let me play with Apple's internal engineering. And I believe that breaking it is actually an act of respect and curiosity towards the people that made this engineering. And physical attacks are still going to be viable for a bunch of time, I believe, because at the end of the day, you can always brute force, and it doesn't matter to you if it takes half an hour to do it, because the shipment would always would take a day at least. And individual researchers which are able to go through all this stuff still exist to this date. However, it's getting tougher and tougher. And at some point, you have to take into account the fact that this takes serious amounts of time. And I do believe the #1 concern for iOS attackers is to strike a good work-life balance, because, I mean, if you do too much live, you're going to not be able to catch up with all these mitigations. However, if you do too much work, you're going to hate this work. So realistically, I do not think this is maintainable, and we'll probably need better jobs. But I would rather wait another few years for that. So thank you for attending the talk. And I do want to thank Apple because, I mean, iOS exploitation is seriously fun, and I do believe it's one of the best platforms to research on. I really do believe it's one of the best things to do with my time, so I really like it. And I also respect all the iOS attackers that are out there, because, you know, I understand what you're going through. And please don't hack my phone. I'm not actually that interesting. And I do want to shout out to Brandon Azad, because his work on PAC was actually really interesting. And I especially appreciate the way he wrote up the process that he went through in order to analyze how these features work, because it's often an untold story. The process of experimentation in order to learn fundamentally black box security features. As much as it might seem trivial for people acquainted with this sort of mentality, I believe it's really difficult to find, you know, stories of people that teach you how to do that. And so I really respect him. I think, yeah, his attack is probably one of the coolest things I've seen in the past few years. And I do want to get people involved into iOS research. Again, I do believe it's really fun. It might seem complex, but things actually make a lot of sense if you understand the big picture. And I do want to thank the Nano development team, because most of my exploits I've actually written in Nano, a significant part of them. And it is the best text editor, and you have nothing you can say to disprove me. So, yeah, Nano. Vim is evil.